This video is going to introduce you to the tools and rules that permit the analysis of energy chains during the preliminary design steps of mechatronic systems. You've received a set of cards describing the usual components of a power system. This set of cards has for objective to help you analyze and criticize, if necessary, an existing system. By giving the functions of each component, or by permitting to verify some design rules, such as association rules, some are true for all domains, others only for electricity or power electronics, and design rules, which are not mandatory but very useful to design systems under certain aspects, such as cost or space envelope. Here's an example of a card's front side. We can find on it the component's name, the power variables, effort and flow, which can be distinguished by the possibility of supplying or consuming positive or negative quantities, in order to know the number of quadrants managed by the component, an effort flow diagram with typical characteristic curves or surface of operating area, and the technological symbol and the associated power variables. Here's an example of a card's backside. We can find on it the functions undertaken by the component. Generally, the component is chosen for one or several functions. During the analysis step, the functions help answer the question, why are we using these components? Then, the operational limits: transient, fast degradation, or continuous, gradual degradation. Also, the associated model, which means the perfect behavior, mostly for transformers. And imperfections, energy storage or dissipation devices. You will have to determine these informations, operational limits and models, during this module. They will help you afterwards in order to prepare the sizing of the system. To illustrate the use of a set of cards and the design rules, we will use the following example of a charger device for mobile phones. The analysis of this device's schematic can help us find the elementary technological breaks which compose the device. Here, the electrical network is connected to an electrical transformer, which brings down the voltage and gives the possibility to have a galvanic isolation. The diode bridge rectifies the voltage in order to supply the mobile phone's battery. More recent chargers are much smaller and have more components. The voltage from the electrical network is directly rectified and filtered in order to obtain a continuous high voltage. An inverter, here presented as an A bridge, but in reality done by a flyback supply, transforms DC voltage to AC voltage. A transformer lowers the voltage. A rectifier rectifies the voltage, which means it transforms it back to DC voltage. And a filter smoothens the voltage to supply the battery. When analyzing a power system, the load and/or the source may not be described by a game card. It's therefore necessary to characterize them as the other cards under the following aspects: power variables, quadrants. Here, we will take as an example a battery charger from the single-phase 220 volts. The EDF network is the power source. The single-phase AC is assumed here to be a perfect sinusoidal voltage source capable of supplying and receiving active and reactive powers. The battery is considered here as a voltage source with a low internal resistance. When there is a combination of several cards or several components, it is mandatory to respect certain rules. The first two rules are to be applied regardless of the device. CR1, similarity of power variables between cards. You cannot directly connect the battery to the EDF network, AC-DC. CR2, the compatibility of force flow diagrams and of quadrants. Regarding quadrants, if one wants to ensure charge function, it needs just one quadrant at the battery. This will simplify the electronic supply. Regarding force flow diagrams, we will analyze here the possible association of a battery with a perfect voltage source, a voltage source in series with a resistance, and a current source. Here we have the voltage current curve for the three cases, 1, 2, and 3. Generating a perfect voltage source from the EDF network is not a good idea. Indeed, force and flow diagrams, here voltage current, may intersect at an acceptable operating point for the battery. Adding a resistor in series or generation of a current source allows us to obtain a reasonable operating point defined by the intersection of the two characteristic curves. For our third connection rule, VAC devices are characterized by active power, useful, and reactive power, describing instantaneous exchange power, but leading to an average of zero. Related components must be able to provide or receive these powers. In our example, we will request that only the charging function, so there is no negative current passing through the battery. The entrance of the diode bridge doesn't request a reactive power. Thus, only the active power is absorbed. The transformer does not change these requests, which can be provided by the EDF network. In conclusion, there is no problem with its installation. The power electronics can minimize losses by using semiconductor switching components, but the use of the switches may result in problems. There are connection rules that helps us avoiding this issue. Never create a short circuit on a voltage source. A voltage source can be a battery or a capacitor that fights against rapid voltage changes. A violent short circuit current can destroy the components. Never open a circuit containing a current source. A current source is an inductance struggling against power fluctuations. At the opening, there is a risk of a very large voltage which could lead to an electric arc. In the same way, never directly connect two sources of voltage or two current sources. It is therefore necessary to alternate current and voltage sources to ensure that the voltage source is never short-circuited and that the current source is never open-circuited. In our example, the diode bridge and the capacitor realizes a voltage source. We cannot directly connect the battery through the switches, and an inductor has been added. Besides the power variables, different symbols are used to graphically represent connection rules. On the two examples above, the alternation between current and voltage sources implies that some components, like an inductive motor, will have to be supplied by voltage source. This voltage source is allowed to rapidly fluctuate around the average value. A converter, as a chopper, does not change the nature of the source, but can generate fast voltage variation. The inductive nature of the motor filters these disturbances, and the resulting current presents low ripples. When designing a system, some rules of smart design can improve the device's quality even if they are not mandatory, contrary to connection rules. They are 1. Minimizing losses. They are 2. Minimizing weight and volume. They are 1. Increases the efficiency, but also enables to respect DR2 by avoiding the use of bulky heatsinks. By minimizing the reactive power Q, which is DR3, voltage or current magnitudes are minimized, and thereby less expensive components can be used. Losses are also limited. By using higher frequencies, the size of magnetic and capacitive components can be reduced. That is why new battery chargers use transformers at a high frequency, around a kHz compared to former 50 Hz, to reduce the global size and price.